Hey CTM students, welcome to 9.3. We're talking about perimeter and area, so a fewer terms than we've been seeing in these past two lessons. We got to know what these things stand for and what they mean. Make sure you're using those extra examples. First, let's talk about the main two things in this lesson. Let's define those things. So perimeter and area. Let's start with perimeter. How do you find the perimeter? If you've taken a geometry course, or it even shows up in Algebra 1, you talk about perimeter in there. Hopefully you remember that it's just the sum of the sides of a figure. So you just add up the sides is another way to think of it. So the sum of the sides of a figure. And what's area? How do we define that? That's more of a region. So it's the region, it's kind of a two-dimensional space, you can think of it like that. The region within the boundaries of a figure. Perimeter will always be in just plain old units, so maybe your units are centimeters or inches. The boundaries of a figure, maybe they're meters, whatever they are. You'll never have a squared, you'll never have a cubed part after that. It's just the units. And then area is always in units squared because you're multiplying one length times another length and you're getting this region by doing that. So to summarize, perimeter, there are some shortcut formulas. You can check those out in the book. Really though, I don't think they're worth talking about in the notes because there's a bit to talk about here, but perimeter, if you just add up the sides, those shortcut formulas really don't save you all that much time. If you want to take a look and find those shortcut formulas and use those, that's fine. But perimeter, I think, is pretty easy to do. Just add up all the sides and you'll have the perimeter. But the area formulas, those are a little more complex, I guess you could say. They take a little more thinking. So here, a summary of areas. So I want you to split this into 3 columns. Make this picture column a bit bigger. The formula one should be a little bit bigger too. The name one can be pretty small. So formula is going to go right here. Starting with a triangle. I'm going to put that here. I'm going to actually write that here, but I'm going to go to rectangle. Leave a good amount of space here. We're actually going to draw 3 pictures of triangles in here, but I want to start with a rectangle. So let's put the rectangle here, and we'll just do freehand pictures for now. If you have straight edges, you can use those, but a picture here for a rectangle. If you have base and height, we're saying that these two things are perpendicular. These two parts. A rectangle has 4 perpendicular or 90-degree angles right there. And what's the area of that? This is where everything is based off of. It's base times height. If you have a square, the book talks about this one more specifically, but a square is just a special type of rectangle. So a square really is still just base times height, but it would be side times side, so side squared. That's what the book has, but it's still base times height. So to go back to the triangle now, think of a triangle as, we'll look here, don't draw this next part, this is just to help you visualize, but if you did this, part in green, don't draw this. If you did that though, what would you have? You would have a rectangle. And so right here I have triangle is half of that. It's half of a rectangle, so your formula should make sense from there, that it would be 1/2 base times height. So the area formula for a triangle is 1/2 BH. Now I said we're going to draw 3 pictures here, so we still have some more to draw here. Sometimes the triangle won't be just like that, where the base and height are directly perpendicular in that manner. Sometimes your height, so I'm going to say this, or you could have a picture looking like this. Sometimes your height might be like this instead. You got a right angle there. This would be your height, the perpendicular height to the base. So here's the base, here's the height. Or you could also have something like this, where the height is actually found by going outside of the triangle itself. Here's your height, this is perpendicular. Your base is just this length from here to here. Remember, when we're labeling things in geometry, put it right in the middle of the segment you're talking about, and that's the segment you're referring to. So I'm not referring to the whole thing from here to that point right here. I'm leaving out the dotted line part. I'm saying that. But you can derive, these formulas are the same. You can still make rectangles that have the same measurements of what you see here, or that have a relationship to a rectangle in the same way, that it's 1/2 of a rectangle. Parallelogram, let's move on to that one next. Parallelogram. Looks kind of like this. This is one example of a parallelogram. And it ends up being the same formula. It ends up being, as for a rectangle, base times height. So the area is the base times the height. But notice they're perpendicular, so they're always perpendicular. Here and here, always perpendicular parts here and here, perpendicular parts here and here. Why does this one work? Again, just listen to this, but imagine I got rid of this, so this is gone, and I put it over here. Well, what do I have? I would have this part moved over to this part, would still be the same length overall. It would still be b times the height here, h, and so notice by getting rid of that, this goes away. I move it over here, and I get a full rectangle that has an area of base times height. Therefore, the parallelogram is the same formula. It's still base times height. Moving on to a couple more, a trapezoid and a circle. Now, a trapezoid's a little trickier, but I have I think a pretty easy way to remember it. Most of these formulas, area formulas and later on volume formulas, I don't really memorize them. I kind of intuitively derive them every time that I think about them. I just think about, okay, what do? I know I do basically this base times height idea, and I apply that to the different shape that I have. But how do I get a triangle? Well, that's half a rectangle, so I remember it's 1/2 base times height. If you can think of how these things are derived, you really don't have to memorize the formulas. You can just think about them, and they automatically pop into your head. So we have the area of this. This is a little more complex, but again, just listen to this part. Notice here, if I were to draw, or if I were to cut this right here. So take this triangle, get rid of that, and then put that right here instead. That triangle would be congruent to that one right here. Do the same thing here. Find the midpoint. We're going to take this, we're going to take this triangle, get rid of that, or kind of cut it out. Imagine that getting cut out and getting put right here. And then right here, the whole thing, what you have left would be a rectangle. So it's again base times height, but what would the length of the base be? Well, it would be the average of the two bases. The length of this one plus the length of this one divided by 2. It's the average of the two bases. That would be the length from here to here. So that would be 1/2 of the two bases added together. That times the height. So that's how I get this formula, or how I think about it. The book has another, I think, pretty clever way to derive the formula using triangles instead of that rectangle idea that I just did. But either way will work to get that. So we have 1/2 B1 plus B2, the average of the bases times the height. Let's put that in our different color down here that I want you to, when you look at this one, this is, I think, the trickiest one to derive of the ones we've done so far. But think the average of the bases times the height. If you can remember that, you remember the formula for a trapezoid, for the area of the trapezoid. And then finally, for here, if we know the circle formula, we should be pretty good to go if we know all the other four that we talked about. So circle, you've got a center point, and you've got a radius. All the way across would be diameter, but the area is pi r squared. And we're not going to talk about why that's the formula so much, but it is still based on the idea of a rectangle and the fact that you could wrap the diameter around a circle pi times. That's where pi comes from. It's the ratio of the circumference of a circle to the diameter of a circle. But let's do one more thing here. Perimeter, I didn't give you any perimeter formulas because really you just add up the sides. That's all it is. So I don't think the shortcut formulas are all that helpful. If you can just remember for perimeter, just add the sides all up, you'll be golden. You'll be good to go. But for a circle, the perimeter of a circle has a special name. So for a circle, its perimeter, remember what it's called? Starts with a C. You say circumference, you got it. Its perimeter is called circumference. And circumference, we usually use a capital C for that. Circumference equals 2 times pi times r. You can also say it's pi times d, so I'll write both of those things down. It's pi times diameter, or it's 2 pi r. So it depends on the situation, what you're given. It's the number of times that you can wrap the diameter around the circle. So it's a distance around a circle. And let's move on from there to some examples now. So we're going to draw, this will be kind of a 6-in-1 example, I guess you could say, but they'll be pretty quick ones. We're going to do one of each. We did plus an extra one with a square. We're going to do the areas of all these different figures that we're going to draw down here. So find the areas of the following figures. Yikes. There we go. Pen stopped working for a moment. Figures. Okay, so first off, let's draw a rectangle. Let's draw that to start. Don't draw your pictures too huge, but don't draw them too small either. You should be able to see what you're writing on here. Let's say this one is without units, so just 12 and 20 like that. Well, what's the formula for that? It's a rectangle. We're using base times height. And so we have A equals, let's write the general formula right now. I think that's a good habit to get into, just to write the letters all out first and then plug in what you know the letters have to equal. And so from here, I would have 12 times 20 or 20 times 12. Really the base and the height, it wouldn't matter which one you picked. Generally we think of the bottom as a base, but it's not always that way. It's just finding a perpendicular part to a perpendicular part. So 20 and 12 are perpendicular to each other. So you have 20 times 12, which would equal 240. So they don't give you units, so you don't have to include units. If you did write units in, if you actually wrote the word units though, you would have to say it's units squared and not just units. I'll put that in parentheses after that, but if there's no units, you don't have to include them. If it includes units though, you definitely should. So here, this one was a, let's as we go, we'll label them in our different color. This one was a rectangle. Alright, how about this one? If I draw a picture like this, and I tell you that these are all congruent and these are all 90, what would you say to that? Hopefully you would say that is a square. That would be correct. You said square. So this is a square, and let's put in some measurements here. Let's say this is 7 meters here and here. I really didn't have to say 7 centimeters or 7 meters both places, because it's a square, we know they're all the same. But we can still use, it's a special type of rectangle, so we can still use base times height. So we just have 7 times 7. If you just said 7 squared right away, no problem, that's fine. That's your s squared. You can always use that. You can also use that as a formula for the area of squares. So we have 49 meters squared for this one. This one, units were included up here, so we need to include those units down here. So let's do another one. This one we're going to make a triangle. I'm going to tell you that this, the perpendicular part right here, is 4. I'm going to say that this is 3, this is 5, this is 10 right here, and this is 4 radical 29, 4 times radical 29. So first of all, let's figure out what kind of shape is that, what kind of figure is that. Well, that's a triangle. So we know it's a triangle, so we know that we're going to use the 1/2 base times height formula here. So we have that to start. So find perpendicular parts. So that's what you're looking for. 5 is not perpendicular to anything. It's not saying that's perpendicular here to any one of these sides, so don't use that. We're not going to use this either. We're going to use the 4 that's perpendicular to this part. Now is this just 10? No, 10 is from here to here. Since it's in the middle of that segment from here to here, we're assuming that 3 is from here to here. So the whole base, we need the whole thing. Trying to trick you a little bit in this one, but did you catch the trick there? You add these up. We got 3 plus 10. That's the length of the base. That times the perpendicular height, that would be 4. So we have 1/2 of 13 times 4. The commutative property of multiplication says you can multiply in any order if that's all you have is multiplication. I can do 1/2 times 4 first. That would be 2, and 2 times 13 would be 26. No units given once again, so I can just say that's it. If you did write units, you would have to write the word units and then square that. Let's do a trapezoid. Let's draw a trapezoid in here. I think I might have forgotten to put that. I did. So on this one, on the trapezoid general formula, put arrows right there and right there. We would have to know that to be assured that it is actually a trapezoid. So let's put that in there as well. Parallelogram, let's do the same thing. So these two are parallel, and this one is parallel to this one. Notice I used a different number of arrows here than I did here because I'm saying these two are parallel with respect to each other and these two, but not this one to this one. They clearly cross right there. So different numbers of arrows mean they're parallel to their respective counterparts that have the same number of arrows. Trapezoid time though. Back to the problem. What makes a trapezoid a trapezoid? Well, you have to have two parallel sides, one pair of parallel sides. Let's say this is 10 feet. Let's say this is 12 feet. We're going to say this one's 8 feet, and that this is perpendicular right here. So let's give it a name. It's a trapezoid. And let's figure it out from there. So we know the area is the average of the bases times the height. So if I plug those things in, I've got one of my bases. It doesn't matter which one I pick first because the commutative property of addition says I can flip-flop the order. It doesn't matter. We've got 10 plus 12. We have that inside the parentheses here times 8, so times 8. So we're going to have 1/2 of 22 times 8. Half of 22 would be 11. 11 times 8 would be 88. And this one does have units, so we need to include those. It's feet squared. Let's do let's figure out what this is. What kind of shape is that? That's my not best work, but that's my freehand circle right there. So let's say this is 9 centimeters. And we'll label that as a circle. What's the area of a circle again? If you forgot, you can go back to your formula table here. Pi r squared, we're using that for this one. So area is pi r squared. And I would have 9 for my radius. It's already right there. This would be 81 pi. This would be an exact answer, 81 pi. And we could leave it like that if it didn't say we had to round to a certain number of decimal places. 81 pi centimeters squared. Now, if it says to use 3.14 as pi, go ahead and use that. But if it doesn't say that, I want you to use the pi button on your calculator. That will give you a better answer. So if we do that here, 81 times pi, I have a pi button on my calculator. There it is over here. You should have one on yours if yours is a scientific calculator as well. So a much better decimal approximation. Remember, pi is an irrational number. It goes on forever. The decimal doesn't repeat or terminate. That is a very good answer right there. We'll round it off to 2 decimal places for now. 254.47. So 254.47. This would be an approximation, so I put a squiggly equals sign right there to say it's approximately that. So we have an exact answer, an approximate answer. It depends on the situation, depends what they ask for in the directions. If it says give an exact answer, you would leave it like this. If it says you can approximate, something like this would be more appropriate. And then finally, let's do the one we haven't hit here yet? What is that? Well, it is a, what does this look like to you? I hope you say a parallelogram. So parallelogram, let's say this is perpendicular right there. I'm going to say this is 13 right here. I'm going to say it's 15. That's the whole thing from here to here, and then this one's 12. Let's give that the appropriate name, a parallelogram. Try to spell that right for me. 2 L's and then 1 L later, and then we've got the area is just base times height. Remember, it's just a rectangle with a triangle. If we move that over here, we get a rectangle. And so this is base times height. What are the perpendicular parts? Again, look for the perpendicular parts. It's 15 and 12. It is not the 15 and the 13. The perpendicular parts are 15 and 12. So if we multiply those together, we should get 180. No units given. That is sufficient right there. If you say the word unit, you better put units squared to be precise, to be right. Alright, so that'll do it for the areas. Remember perimeter though, just to talk about that quick, how can we find the perimeter of this? You just add 12 plus 20 plus 12 plus 20. You could also think of it as 2 times 12, because there's 2 12s, and 2 times 20 added together. Here you could say 7 times 4, or just 7 plus 7 plus 7 plus 7. Here you would add up all these sides. Here you would add up these sides. This would be 13 and 15, property of parallelograms. For this, you'd do 2 pi r. So you'd do 2 times pi times 9. You'd get 18 pi. And you could approximate that in a calculator. Here, you would have to know what this side is to figure out the perimeter. But we don't have that given here. But that's how we would find it. We would have to add those 4 things up. So perimeter, just add up the sides. You're good to go. And now, perhaps, the most well-known theorem in the world, the Pythagorean theorem, named after this guy. This is Pythagoras. He wasn't the first one to figure out that it worked, but he was the person we give the credit to as somebody that formally defined it or formally proved the Pythagorean theorem actually works in all cases, not just for specific examples. So he gets the credit for it, even though we knew about it before him. There may have been some other cultures that had actually proven it too. I'm not totally sure on that, but he's the one that gets credit for it at least. So Pythagorean theorem. It says in a right triangle. You should double underline that. It has to be a right triangle. If you don't have a right triangle, you can't use the Pythagorean theorem. Now students will tell me a squared plus b squared equals c squared, Mr. Wagner. They'll tell me that. I say that, yep, that's right. But what do a and b and c stand for? And then some of them just give me this blank stare. And they're like, I have no idea. So this is how I want you to remember the Pythagorean theorem instead. If you know a squared, b squared, c squared, great. But it's leg squared plus leg squared equals hypotenuse squared. That's what I really want you to remember. If you can remember that, then plugging in the numbers correctly and solving for the missing parts will be very easy. So what are the legs and what's the hypotenuse? Let's draw a right triangle off to the side of this. Here's a right angle right there. Let's say this is A and B, and that this one is C. If that's the case, then these two are the legs. This one is a leg right here, this one is a leg right here, and this one is your hypotenuse right here. That's where a squared plus b squared equals c squared comes from. So here now we can say, based on the picture that we have, this would be true. That's where this comes from. You can think of it like that. So it's still here, leg squared plus leg squared equals hypotenuse squared. I want you to remember it like this though, because those letters won't always be the same. They could even switch the letters around on you. They could make them Greek letters. They could make them just crazy symbols. Whatever you want for a variable can go in here, here, and here. But the legs are always the perpendicular parts, and the hypotenuse is always across from the right angle. Let's make a little note of that right here. So hypotenuse always is across from the right angle. It's also always going to be the longest side. So if you ever get a hypotenuse that's shorter than the two legs, you know you messed up your math somewhere. All right, let's check out a second example. This gets its own page. It's that important. Thanks, Pythagoras. We appreciate your theorem. I think it's not at all intuitively obvious that this would actually work. A squared plus b squared equals c squared. Leg squared plus leg squared equals hypotenuse squared. But pretty cool. We can prove it. There's this famous book with over 400 proofs, if I can remember right. 400 valid, different, unique proofs of the Pythagorean theorem, different ways to prove it. One of the proofs even comes from one of our presidents of the United States, James A. Garfield, gave a correct proof he's credited with a unique correct proof of the Pythagorean theorem. So solving for x here, going to give you two right triangles, and we'll solve for x in both of them. Let's say this is 5, this is 12, and this is x right here. And over here, let's draw another right triangle. This one I'm going to put on a bit of a tilt, you could say. But something like this. This time, here's the right angle. Just because I orient it different, though, doesn't mean that changes anything. Let's say that's 20. And this is x. This is 20 centimeters. I'm going to give this one some units. This is 30 centimeters right here. So these are not necessarily drawn to scale. You notice this looks pretty close to this, but this would actually be much longer than that right there if that's 12 and that's 5. So a good point to bring up here again is that you can't trust the way the picture looks. You have to trust the information given in the picture unless you're told that it's drawn to scale. So here, what are the legs? Let's identify those here first. The legs come together to make up the right angle. The hypotenuse is always across from the right angle. So this would be a leg right here, and so would this. Let's label those things here. And this would be hypotenuse. Over here, here's your hypotenuse across from the right angle. Here's a leg, and here's a leg. And so now that we have that established, we can use Pythagorean theorem very easily, I think. So we have 5 squared plus 12 squared, leg squared plus leg squared, equals the hypotenuse we're calling x here, equals x squared. Let's solve that now for x. We have 25 plus 144 equals x squared. It means we have 169 equals x squared. From there, let's use our different color to show that we would take the square root of both sides, then the squares and square roots would cancel. We'd be left with 13 equals x. No units are given, so we can leave that out. But I'll have you write units in parentheses underneath. Is it units squared or units cubed or anything like that? No, it's just a length. The lengths are just plain old units. Over here, what's a leg squared plus leg squared? It would be x squared plus 20 squared. If you said 20 squared plus x squared, that's also valid, not a problem. But you have to have equals 30 squared on the other side. So let's simplify this now. You would have 400 right here. We would have 900 right here. If you subtract 400 from both sides, that'll cancel right here, and we'd be left with x squared equals 500. So same thing as before, take the square root of both sides. The square and square root cancels. You're left with x equals the square root of 500. However, we should get this in simplified radical form if we can. And so we can break this down. The largest perfect square that's a factor of this is actually 100. 4 would go into here, but so would 25, and 4 times 25. Remember, looking for the largest perfect square that goes into there. 4 times 25 would also be a perfect square. 100 is a perfect square. So 100 times 5, and now the 100, this would come out. We could pull that out. The square root of 100 is 10. And so we'd have 10 times radical 5. This would be an exact answer, centimeters, because that's my units up here. So an exact answer right there. If you approximate that, let's get out our calculator for that. So 5, if I'm going to take the square root of 5, there's the square root button. So the square root of 5 is that times 10. It's just going to move the decimal one spot over, 22.36. And so here we could say this is approximately 22.36 centimeters for x. So exact answer, approximate answer. Again, it depends on what they ask for. If it says you can approximate, or it doesn't say at all, something like this would be fine. But if it says give an exact answer, you would leave the radical in there and do simplified radical form. So that's the Pythagorean theorem, a quick synopsis of that. Now let's do a couple of real-life examples where we apply what we've learned here. And let's talk about, if you're hungry, I'm sorry, we're going to talk about some pizza. And you're going to have to stare at this picture of pizza. If you don't like cheese pizza, then maybe that's not quite as hard for you to look at. We're going to talk about pizza and see what the better price is, or what the better deal is. I wondered this as I was your age growing up, like, okay, so this one cost a lot less, but am I really getting a better deal? This one costs more, but like how much more per square inch is kind of what we need to think about. So the following circles represent pizzas. We're going to draw some circles down here. Pizzas at the given prices. So there's no prices. I'm not saying you need to draw this stuff. This is just some things to look at, to refer to. Which is the better deal? So when they say something like that or equivalent to that, what they're really asking is per square inch, what's the better deal? So let's put that in parentheses after that. What's the better deal per square inch? So let's draw a couple of pizzas. We're going to have a 12-inch diameter one, which they left out here for some reason. They didn't include that. I guess they don't have that as one of their, at this particular pizza shop, pizza parlor, pizza place, pizza establishment. What else can I come up with? This one's going to be a little bit bigger. This one will have a 12-inch diameter. This one will have a 16-inch diameter. When they sell pizzas, that's generally how they do it. They'll say this is a 16-inch pizza. What they mean by that is that it's 16 inches all the way across the diameter, 16 inches. So here we've got two different problems basically to figure out. Let's say this one was $10 and that this one was $15. So what's the better deal per square inch? And notice this is not drawn perfectly to scale. You can tell that by the bumpiness of my circles here, but just assuming that it's decent, at least I feel like it's pretty decent in terms of scale and scale factor. Which one's going to cost more per square inch? So what's the better deal? You might initially say, well, this one because it costs less, but is it really? Is it the better deal? Let's figure this out. How do we figure out per square inch? Well, we'd have to know what the whole total square inches is, and then divide that into the price. And so let's figure out the area first of each pizza. So let's split this into two columns right here. We've got pi r squared. So pi times the radius is going to be 6. This is just coming from this divided by 2. And so let's show that in a different color. Circle this, make a little arrow there, and put a little divided by 2 next to that. Same thing is going to happen over here. We're going to divide by 2 to get the value over here. So it's pi r squared. Don't forget your squared right there. And here we have area is pi times pi, pizza pie. How appropriate. But pi times 8 squared. We're dividing that by 2 to get that number. So what do we have? We've got 36 pi right here, and we've got 64 pi right here. So notice, almost 2 times bigger. So with that said, I'm starting to lean this way, that this is going to be a better price per square inch. But let's figure out what this is approximately. I've done this work already, so I'm just going to tell you what I got. This is 113.10 inches squared. This one about 201.06 inches squared. So that's some important information. But per square inch, that's what we're really concerned with. So per square inch, what do we have here? Per square inch, what do we have over here? So this would be, excuse me, this would be approximately per square inch. The cost per square inch would be cost on top divided by square inches on the bottom. And you put that into a calculator, 10, and divide it by that, you get approximately, it's going to be a decimal here, about 8.8 cents or $0.088 per square inch. So a very important piece of information there, not final answer, so I circle those things. I'll box in my final answer. So here I've got 15. Let's put $15. Let's put $10 there. So we have $15 divided by, this is approximately equal to 201.06. Put that into a calculator, you end up getting this. It's about 7.5 cents or $0.075. So another important piece of information right there. Which one's the better deal? It looks like this one costs a little bit less, about 1.3 cents less per square inch than this one. So if you are looking for the best bang for your buck, this is the best bang for your buck. However, if you're somebody that's going to eat half the pizza and just throw the rest away, this is going to be the better deal for you. If you're that kind of person, if you're just going to throw stuff away, don't do that. That's called ORT, O-R-T, leftover or wasted food. Don't throw your ORT away. Save your ORT. Put the ORT in the fridge. Eat the ORT the next day. I didn't make that up. I used to work at a camp. We would do the ORT report. It was a math and science camp. It was awesome. We did the ORT report. If the kids had no ORT for a whole meal, then we would be really excited. If they had no ORT for the whole week, we would have a pizza party, actually. How appropriate. Pizza, ORT. We're talking about pizza here. So since the 16-inch pizza costs less per square inch, it's the better deal. So especially if you're going to feed a large group of people, get the 16-inch pizzas. You're going to be able to feed more with less money for it. So it is the better deal. And now a fourth example, a final example here. I think I'll use my tool shapes here. So I'm going to draw a rectangle to start. Leave a little space to write an explanation of the problem here, but draw a rectangle, kind of like you see here, about in a 2 to 3 ratio. This is 2 compared to 3 right here. And let's draw a triangle in here as well. This one I'm going to use this for. This is not necessarily drawn to scale, but I'm trying to draw it as close as I can to scale without getting an actual ruler out. And then a circle. I'm going to insert a circle in here. Alright. And this is going to be a right angle right here. I'm going to tell you that this all the way across is 10 feet. And right here is 12 feet. And right here is congruent. This and this are congruent to each other. So what could we say about a few things here? Before we get into this, I'm going to use green for this because I'm going to pretend this is grass, but you use your different color. If you were using red or whatever color, just use that. We're going to shade in the non-circle and the non-triangle part of the rectangle. So shade that in your different color. Again, this is representing grass, that's why I'm going to use green here instead of my normal red. So we're going to fertilize this grass. And we go to the store and we notice that it says it covers this much square feet of lawn. And so, okay, we're like, how many bags then do I need to buy? I just came all the way across town to buy these bags of lawn fertilizer. I don't want to come back here and return stuff or come back because I didn't get enough. I want to make sure I get the right amount so I don't waste money on gas or waste money on getting too much and buying too much. So let's see what we got here. This is going to be 24 feet from here to here, and this is going to be 36 feet. This is a pretty small lawn, I would say, so this is just a tiny little area here, 36 feet. It's just 12 yards by 8 yards. Not very big, but let's say that's what you had. Maybe you have a little bird feeder or bird bath here or something like that. Maybe you built a little triangular, I don't know what this would be for, birdhouse maybe, a triangular birdhouse. And so you don't need to put grass here or here. You're just putting grass around there and you're just fertilizing that area. So this little guy, he's going at it. He is fertilizing that lawn. But did you buy him enough? What are you paying your little kid doing the work here. Maybe you're paying him $5 an hour. I don't know. It's good money for a little guy like that. Maybe it's good money for you. I'm not sure. Would you like to make $5 an hour? I've got some work for you. You could do some work for me. I'd be willing to pay you that, I think. So this one right here, this is also going to be 12 feet since it's congruent to this one. Same number of tick marks. So we can mention that right here. And what we're going to try to find here is the shaded region area. So determine the area of the shaded region. So I see 3 different shapes here, and those 3 shapes, I know how to find the area of each one of those separately, and I just need to put them together in the right way. I see a rectangle, a big outside rectangle, and I see a circle, and I see a triangle. I know how to find each one of those separately, and so the area of the shaded part would just be the area of the largest outside shape, the rectangle, and from that I would subtract the area of the triangle and the area of the circle. Simple as that. So that minus that minus that. Now what is the area of the rectangle? What is that formula in general? I'm going to use some brackets here just to keep things hopefully a little easier to follow. This rectangle would just be base times height of whatever the rectangle's base and height is. The triangle would be 1/2 base times height. This is now referring to the base and height of the triangle, which may be different than this BH, so just keep that in mind. And the circle, the area of the circle is pi r squared. So we take this minus this minus this, that will give us what we need, our final answer. So let's say, or let's look at this. We've got, I'm going to keep my brackets for now, just to keep the parts distinct and separate and hopefully easy to follow. This base and height is 36 and 24. I'm going to tell you, we can assume that this was a right angle. So I'm saying you can trust the looks of the picture on this one. So it's 36 minus, or times 24 minus, now 1/2, what's the base and height of the triangle? Look for the perpendicular parts, it's just 12 and 12. So we have 12 times 12, you could even say 12 squared, and you'd be fine in that case. And here, minus pi times the radius is going to be half of that. The radius is going to be 5 right there. So minus 5 squared. From here, let's work it out. This would be 864 minus, you'd have 144 if you did, there we go, did 12 times 12. You could also think of 1/2 of 12 is 6, 6 times 12 is 72. So either way or any way you do it, you get that, and here you'd have 25 pi. So let's combine like terms. The plain numbers, the constant terms can go together, but not the pi parts yet. I want to leave that exact as long as I can. This minus this would be 7. $792. We have 792 minus 25 pi. If you were asked to give an exact answer, you'd be done right there. You can't put this and this together. It'd be like putting something with an x and without an x together. But the pi does represent 3.14159, etc. But if we put that into a calculator, take 25 times pi, you'd get 70 something and some change. Let's see what that is here. So we have 25 times pi, 78.539, so on. So we take that, subtract it from 792, and we're going to get our answer. We would get approximately 713.46. So feet squared here, feet squared here. This is the area of the shaded part. So depending on how much one bag of fertilizer covered, maybe you have enough with one, maybe you need more. But if you knew that going into the store, then you don't have to waste your time going back to the store. You don't have to waste your money paying more for gas. You calculate it first, you know what you need to get before you go, and you just saved yourself time and money. Boom. Just like that, math becomes practical, math becomes useful, and I think math just saved you some money. That's right. Okay, so from there, there's one more thing I want to say quick. There are some other examples in the book. I don't want to make this too long here, this lecture, so I want to just point you to these. Last thing to write down, I want you to check these out. So I want you to actually do this for me if you're one of my students, and do this right now if you have your book with you. Well, let's do it as soon as you get access to a book. Just read over these problems for me. Check these problems out on pages 500 to 503 for more word problem examples. So do that now if you have your book. If you're not, get that book as soon as possible. Read those over so that you can see a couple other types that you might see. The two that I did were very similar to the two of them in the book, using some different numbers, some different shapes. There's a couple of extra ones in there that I think you'll find helpful as you tackle problems like this. That'll do it for me here. That'll do it for you as well if you're taking notes here. Hopefully you found that a good either review or refresher on perimeter and area, or a good introduction to it. Either way, have a good day. I will see you later.